Okay, so welcome to lecture 56 in this course of Classical Mechanics 1. So, we are towards the end of this course. So, we are going to start the last topic in this course, which is called small oscillation. So, remaining 5 lectures will give in this small oscillation, and we plan to learn that let me list down the general coupled oscillator. So, general coupled oscillator, then eigenvectors, eigenfunctions, normal modes, normal oscillation, and vibration as an application, vibration of linear carbon dioxide molecule. So, this is the plan for this last topic, this last week of this course. So, before we begin, so let us mention that why we are studying small oscillation, or rather all the time we talk about simple harmonic oscillator. So, simple harmonic oscillator, all the time we talk about simple harmonic oscillator. Why? So, my question we start with why simple harmonic oscillator is so important in physics. So, let us start. In usual class, I generally wait for the student to reply, but it is an online course, so I cannot get your answer, but just think for few seconds, or couple of minutes, that why simple harmonic oscillator is so important in physics. Okay. So, this reason is very simple. Reason is that any potential, say one dimensional, just talk about everything in one dimension, and one dimensional simple harmonic oscillator, any arbitrary potential Vx which has some minima, say at x equal to a, will have a simple harmonic oscillation around the minimum. So, we will have, let me complete the sentence, we will have, so any arbitrary potential in one dimension Vx which has a minima, say at x equal to a, we will have a simple harmonic oscillation around the minima. So, let me visualize this in more detail. Suppose you have a, so let us plot. So, you have Vx versus x, and suppose you have a kind of arbitrary potential. Okay. So, now you can see that this potential has a minima here, say at x equal to a, it has a minima. Around this minima, if you consider small oscillation around this minima, you will find a simple harmonic motion. So, simple harmonic oscillation around this minima. So, suppose if you see particle can be in equilibrium in the where the energy is minimum. So, particle can be equilibrium in this minima or in this minima, and around the equilibrium you will find that the motion is a simple harmonic motion or oscillatory motion. So, that is why the small oscillation is so important, that you can arbitrary potential you can study around the equilibrium position can replace by the simple harmonic motion. Similarly, same thing can happen for the other minima if present. And mathematically this can be seen very easily. Suppose you have V, suppose you expand this potential around x equal to a minima. Suppose x equal to a is a minima. So, if x equal to a is a minima, dv dx at x equal to a should be 0. Okay. So, if we expand this in a Taylor series, you will get Vx equal to V at the minima point plus x minus a whole x minus a not whole square dv dx at x equal to a plus x minus a whole square by 2 d2v dx square at x equal to a and higher order terms. But I already said that x equal to a is the minima of the potential. So, this term is 0 as x equal to a is minima. Okay. Now, we have, so up to second order term Vx is your Va x minus a whole square by 2 d2v dx square. This is a purely x independent term, because the double derivative has to be calculated at x equal to a plus higher order term. So, if you consider small oscillation, higher order terms you can neglect. Now, this is a constant term, this is constant term, and without any loss of generality, you can consider Va to be 0. That is by choosing the 0 of your potential energy. Okay. So, this we can always do. So, your Vx, now you can see your Vx is some constant, say k. So, let us keep that k half k x minus a whole square, where k is equal to d2v, the double derivative of the potential at x equal to a. Okay. So, now this is a simple harmonic oscillator potential. Simple harmonic oscillator potential, and you know the frequency of this oscillation. You can find this frequency of oscillation. So, it will be oscillation. So, this describe, so if I write a Lagrangian will be half m x dot square minus half k x minus a whole square, or you can write x minus a equal to say capital X. So, half m x dot square minus half k x square. This is a harmonic oscillator Lagrangian, and the frequency of oscillation is root k by m. So, in this case the frequency of oscillation around the minima point will be root. Now, k, if you substitute d2v dx square at x equal to a by m. Okay. So, the frequency of oscillation is k by m, so that you can find. So, this is a very interesting result in this sense, that if you have a potential which has a minima, around that minima you will find a harmonic oscillation, and the frequency of that oscillation is given by double derivative of the potential at x equal to at the minima divided by m. So, that means around the equilibrium or close to equilibrium you can have a harmonic oscillation for any arbitrary potential. So, to illustrate this simple concept, let us consider one example. So, this kind of question also asked in different competitive exams and as a MCQ question. So, suppose you have a potential, say one dimensional potential to x cube minus, say I have chosen carefully such that we can have a easy solution. Suppose you have a potential V x equal to 2x cube minus 9x square plus 12x plus 5. Okay. So, now if you have and you are, suppose the question asked is that find the frequency of small oscillation around the minima of the potential. Or suppose some particle is moving under this potential and it is in equilibrium. If you disturb that particle from the equilibrium little bit, it will have a oscillatory motion, and what will be the frequency of oscillation that you have to find. So, for competitive exam you directly find the minima. You first find the value of A, that is the minima of the potential, and then directly calculate d2v dx square at x equal to A, and then it is divided by m and you can find. So, let us do this problem systematically. So, to find A, you have to find dv dx at x equal to A will be 0. So, this is the condition for extrema or to find the minimum. So, if you differentiate this function potential, it will be 6x square minus 18x plus 12 equal to 0, or x square minus 3x plus 4, now 2 will be equal to 0. Okay. So, this has obvious solution at x equal to 2 and x equal to 1. X equal to 1 it is 0, 2 also it is 0. Okay. So, this is the solution. So, these are the 2 points where the possibility of minima happening. So, now we need to derive this double derivative also. So, which is actually true minima, that we have to see. So, d2v dx square will be 12x minus 18. Now, this quantity, so d2v dx square at x equal to 2 will be 24 minus 18 equal to 6. So, it is greater than 0. So, x equal to 2 will be the minima. Let us check whether x equal to 1 is also a minima, but it is not, that you can immediately find d2v dx square at x equal to 1, you will find it is 12 minus 18. So, minus 6, which is less than 0. So, x equal to 1 is a maxima of the potential. Okay. So, we have to find, so we have found that x equal to 2 particle at around x equal to 2 particle can have equilibrium and it can have a oscillatory motion. So, now you also have calculated d2v at x equal to c. So, this will be d2v dx square at x equal to 2 is 6. So, the frequency around the equilibrium, which is the minimum of this, will be root over d2v dx square by x equal to a by m. So, if m is the mass of the particle, then it will be substituted here. So, it is 6 by m. Okay. So, frequency of oscillation will be root 6 by m in this case. Okay. Okay. So, now we will consider a more general case for this. Okay. So, it is a system. So, now we will make this analysis in more general framework. So, suppose a system, when is the equilibrium? So, a system is in equilibrium. So, we consider to be in equilibrium if the generalized force, if the generalized force on the system is 0. So, there is equilibrium means no force. If there is a force, there will be disturbance and it cannot be. So, if you have a conservative type of system, then you have this force is minus del V del Q equal to 0. So, will be the equilibrium. So, now let us see, we are in a general framework. So, Q equal to Q 0 K is the, so let Q 0 K is the equilibrium coordinate. Is the equilibrium coordinate. Okay. And we want to, we have a general system. So, we are talking about general system. So, general system, the potential is Q1 to say Qn. So, you have n degrees of freedom. So, you have, and this Q, when we put a subscript 0, and that will be the equilibrium position. That means that Q01, Q02 to Q0n is the equilibrium position. In that position, there is no force acting on the system. Okay. So, but we have to know that equilibrium is stable or unstable. So, next we will learn about stable, unstable, stable or unstable equilibrium. For that, what we will do, suppose visualize this in one dimension. So, suppose you have a potential looks like this or looks like this, right. And if this we will call a stable equilibrium, if we disturb the particle little bit from its equilibrium, it will restore to the position. Particle will pull back to the position. Then it will call the stable equilibrium. So, if I want to disturb the, if you want to disturb the particle from here or in this direction, then it will be pulled back. But what will happen to here? If it disturb little bit, then particle will not be pulled back. It can fall down to this. Or if you disturb in this direction, so it will move in the direction of disturbance. So, this kind of situation is stable equilibrium. And here small disturbance will throw the particle from this position, will unstable. And we can see that stable equilibrium is actually true, corresponding to true minima of the potential, and unstable equilibrium can be the maxima of the potential. So, it is not the true minima. So, what happened, that force is basically the curvature in the potential. So, if you see that curvature is positive here, and you will find that force is del V del x. So, it is a negative force, restoring force. Okay, so, depending on the curvature of the potential, you can also find the minima and stable equilibrium and unstable equilibrium. Okay. So, that is the stable equilibrium and unstable equilibrium. So, if it is unstable, if slight disturbance to the particle will throw the particle out of the position, and if it is a stable equilibrium, then it will be considered that when you disturb, it will pull back to the. Okay. So, with this, let us now try to expand the general potential around a equilibrium, say. Okay. So, we had potential V q1 to qn, and we are expanding. So, expanding the general potential around the equilibrium, which we denoted by 0 1 to q 0 n. So, this is the similar thing we have considered in one dimensional motion. So, this will be, so V at the equilibrium. So, let us denote it by q 0 I plus now sum over k del V del q k, and this has to be calculated at q k equal to q 0 k. Okay. And for the all, so all first derivative and times q k minus q 0 k. Okay. Now, second term will be double derivative. So, sum over, so half will be there, j and k. So, let me write del 2 v del q j del q k, and this has to be calculated at q j equal to q 0 j and q k equal to q 0 k times. So, I could not finish the all terms, some times q j minus q 0 j times q k minus q 0 k. Okay. But as I argue for the one dimensional case, without any loss of generality, you can choose your coordinate system in such a way that you can choose your equilibrium point as the 0 point. So, let us choose. So, without any loss of generality, let us choose the equilibrium point point at the origin or origin of the configuration space. Okay. So, so we can take that q 0 I to be 0 for all I 1 to n. Okay. So, this for simplicity. So, now the potential, so arbitrary potential now boils down to a that at the 0 position plus half del 2 v sum over j and k del 2 q j delta q k q j q k. Okay. Here I want to mention that because this is the minima, we are the equilibrium position. So, it will minima. So, this will be del 2 v del q k for q k equal to q 0 k is 0. So, this term will be 0 for because these are the minima. Okay. So, now what will happen that this is a constant term and can be considered to be 0 by choosing your the potential position, the 0 of the potential. So, now V in the simplified version I can write as half sum over j k v j k q j q k, where v j k will be del 2 v del q I del q j, this is k. Okay. And you can see that we can interchange the derivative. So, v j k is v k j. So, this is the symmetric, because we can order of derivative you can change. So, v in a matrix form, because it is a general case. So, v will v 1 1 v 1 2 and dot 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 to v 1 n, similarly v 2 1. So, this will be a symmetric matrix. So, this is the potential term, and since today we do not have time. So, in next class we will also consider in the similar fashion the kinetic energy term. And we will write a general Lagrangian to find study the small oscillation. So, let me summarize what we did. We consider first with the why simple harmonic oscillation is important. Then we argue that any potential with respect to its minima can be around its minima, which is the equilibrium, can be thought can have a simple harmonic oscillation. Then we are considering a general case, and we have seen that potential term can be written in terms of a symmetric matrix that will come back to this. So, this is the equation. Now, we will write the kinetic energy term in a similar fashion, and then we will study the small oscillation in a general framework, and we will later with that find the normal modes, eigenfunction, eigenvalues of the frequencies. So, let us stop today, and next class we will continue from this point the general formulation of small oscillation. Okay, bye for today.